All right. Hello again, everyone. Hope you have had a nice week so far. As you might have seen my email, I extended the deadline for assignment number 2 by 1 day, so it's going to be due tomorrow by midnight. Any question before we start? All right. I have put the lecture materials for today on the iLearn webpage, our course webpage. And I'm going to give you a little tip or part lecture on the MPV because a couple of students have questions about that on our office hours. So I kind of felt that it would help other students as well. You have already must have seen the MPV example on Excel that I have put on the assignment, attached to the assignment, but we're going to go through it again. Right. Okay, so NPV stands for net present value. And it's, you have seen it in the assignment if you have tried the assignment. So suppose that you have a series of cash flows. So if you're familiar with economics, if you have taken any economic course, hopefully you have, you have then time periods, for example, this month or this year, then next year, next month, or next period, whatever your period is, weekly or monthly, generally a weekly, monthly and yearly, then you have the values are dependent to that period because if you bring them to, for example, today or another actually time period, the value is going to change because the money is time period dependent. For example, because of the interest rate or because of the inflation, whatever that is there, that's the main concept. Okay, so suppose that we have a series of periodic cash flows as you see here, year 1, year 2, year 3. Cash flows can be positive and negative. Positive when those are for incomes or revenues, and the negative ones are for expenses or costs. Okay, so we could have either of them or both of them mixed together. Okay. So you see here 3 cash flows here. For first year we have $100. The second year we have a negative $100, $110. That's cost currently. The third year we have $55 positive, so that's also a revenue, positive cash flow. So what we want to do is, suppose that we want to compute the equivalent value of these cash flows at the today value. Okay, so what is the equivalent today cash value of these cash flows or value of these cash flows? That's what we mean by net present value. Right? So you have seen the example how you can actually manually compute that. So we need to have like an interest rate, otherwise if interest rate or if the rate of for the money value is 0, then these values are all in the same. You can just move them what period you want. So the formula is MPV. The first parameter is R, the interest rate, and you have to make sure that interest rate is according to the same periodic value that your cash flows are. For example, if your cash flows are a yearly basis, then your interest rate must be also yearly basis. And it's a little bit tricky because sometimes you get cash flows in yearly or monthly, and the interest rate are either monthly or yearly. So you might have to convert them. Okay? So the first parameter is the interest rate. The second parameter is actually the range of cash flows from, for example, year 1 to year whatever, 20 or 30. So here's another example. Suppose you want to buy a car and you have to pay $5,000 upfront right away and a monthly payment of $300 per month for 5 years and interest rate of 6%. Okay, so it is very important to know whether this 6% is monthly or yearly. Okay, so if it's a yearly, then you have to multiply by 12 to get the monthly rate, and then use it in the NPV function. Okay. So now suppose that you want to see, okay, this $5,000 now, and then monthly payment of $300 for the next 5 years at the interest rate of 6%, how much is it going to cost you in today money? Okay, so that's the NPV, what NPV means. So what you need to do is you find the NPV for the cash flows that you have from the 300 payments of these 12 months for 16 months, 5 years, each month 12. So that's 16 months of 300 payment. Then you have to add that up to the cost, that the payment that you paid upfront, $5,000. Okay, so you have to also make sure to add that one too. Okay? So the cost of monthly payment would be NPV 6% if the interest rate is monthly. So if the interest rate is monthly, use the 6%. If it says that 6% annually, then you have to multiply by 12. Okay? And then the next is the range of the payments in your Excel file. So suppose that they are stored in column A from row 1 to row 60 payments. Then you just put that there. And then you add that up by the $5,000 that you have to pay upfront. But also make sure that you do not get confused by the negative values and positive values, because these are costs. It has to be, both of them has to be negative. So the 5,000 has to be negative value. Here we say the cost is 5,000. That means that the cash flow is negative 5,000. Okay? And then you add it up to whatever you calculated with the NPV. You could also use the present value. That actually has, you don't have to, if the payment is constant, is fixed, like $300 per month for 60 months, then you don't have to actually select the range of 60 rows for one column to do that. With the present value, it would be just present value, the interest rate, the number of payment, which would be 60, and also the payment, which is $300. So you just fix it, because it's fixed, you just put it there. And so if you have seen the formula for the Excel, we open up an Excel file here. We already have it. Right. For example, I am running multiple programs, so that's why my RAM is just jammed and it's really slow to run anything else here. Okay, NPV. So this is the NPV example that you have here. You have the interest rate is 5% yearly, and you have cash flows for 3 years, constant $100, and they are positive. So that means that they are income, their revenues are positive. To compute actually that you could do it manually by discount factor using the formula, but I'm going to skip over that. I'm just going to use the NPV. So this is the NPV formula. So the NPV formula is the interest rate, which is 5%, and the cash flow, which is column B6 to B8, right? Then if you hit that, that's $272.32. Because this is actually the fixed payment of $100 for per period, you could use also the present value, PV. So the PV formula, the rate is 5%, that's the interest rate. And then the number of periods is 3, and the payment is just 100. We don't have future value here. Type is the end of period. We get $272 here, and that considered as negative. So I'm going to, again, because as I said, this can be tricky, so I'm going to put negative value here. So now it considered it as a revenue. So that's its positive. Because the default is payment. Payment is, that means that you pay, so it's a cost. So because these $100 cash flows are positive, then they are not cost, so they are negative of what is cost. So that's what I put here, the formula as a payment. This was PMT, as you see here. PMT, that's payment. So payment is a cost. So that means that if you put 100, that's actually $100 in cost, which is negative cash flow, right? So that's why I put negative 100. So that means that it's not a cost, it's actually, for example, revenue or positive. So this, it can be very tricky. So you have to be very careful. So if I hit click and it works, it completes the sale. It's $272.32. All right. So if I in addition to these yearly cash flow that I had, if I also had something, a payment or a revenue in the, like today, these are like future, like a year from now, 2 years from now, 3 years from now. If I had also a present value, something like $5,000 here, a cost or a revenue, I would have to add it to this value. If it's a cost, I have to subtract it. If it's a positive cash flow, like someone paid me a sums of money, $5,000, then I have to add to it. Okay, so it's very important whether it's a cost, negative value cash flow, or it's a revenue, it's a positive. Payment, that means it's actually negative. But if you're using it for a positive cash flow, you have to use negative that value. Right? So make sure that you don't confuse that. Any question? So this is kind of for helping you with the question that we had in the assignment, which was for the, I think it was part A for the one-way table that it asks you to compute the NPV. Okay? So it didn't ask you to do the one-way table for the cumulative saving. Okay, it asks you to do it for the NPV for partial payment PPP and the NPV for the FPP, and also the cumulative payment for the cumulative saving for FPP and PPP. So you must have 4 columns, and the parameter that changes there was the gross rate of price gross rate. Okay, any question here? Hope that cleared that up and help you, those who haven't done the assignment, one who have already done it but could use some help here, use this information. Any question? Right, so I'm gonna close this. Close this one. So we're gonna go to the lecture optimization. So if you remember last time, we introduced the optimization concept and topic that we said that we're gonna continue cover it for the next 8 to 9 weeks. So I'm gonna go to the second part. All right. Okay. So optimization using Excel solver. Just to recall, we had this problem which was an investment problem, small investment problem. So what we wanted to do, just to recap, to update you on, bring you to the same page. We wanted to optimize our investment plan, which was our profit. So the problem is you want to invest in a stock market and you have $1,000 budget. That's the whole budget that you can spend on the stock, and you have narrowed down your choices to 2 stocks, A and B. Okay, but you also have some other constraints. For example, for any reason you don't want to spend more than $700 on a stock A, and you don't want to spend more than $600 on a stock B. Okay, and suppose that the rate of return for a stock A is 6%, its price is $4 per share, and the rate of return for annual rate of return for stock B is 9%, and its price per share is $6. So you want to plan an optimal investment so that after a year, by the end of 1 year, your investment return would be maximized. So this is a kind of an optimization problem that we solved it actually using graphical method. And I actually showed you how we can actually model this and solve it using Excel solve. So this is what we want to go back. All right, let me go back on the Excel and show you in the Excel what we have in Excel. So this is the model that we have. Let me show you. This is, by the way, already uploaded on, I don't know if you have access to it. So this is how we set up the model. We have an Excel file here. I have created a sheet called model, and this is how we follow the format. This is the name of the problem that we're solving, a simple investment programming problem. Then these are our input. We have two options, a stock A and a stock B. And we have actually a couple of information here, price per share here for each stocks, $4 for stock A, $6 for stock B, and there is the expected rate of return here. And here in the investment plan, this is our decision variable. This is how much you want to buy from a stock A, and how many shares of the stock A and how many shares of stock B you want to buy. So this is our decision variable. And this is the problem that we set up, constraints and objective value. Okay. So in constraints, we have a stock A and a stock B in the total. So for stock A, this is just going to show you how much you want to spend on a stock A. So for a stock A, we said that you should spend more than $700. So that's just the price per share multiplied by how much you buy, which is right now 0. So that would be less than equal to 700. So this is kind of implementation of what we did before. I'm not going to repeat this again. And after you have put your model here, we go to the data tab and then the solver here. And then the model is over here. I have put it here. You see that here. And then you click, make sure that this is maximization problem. This is your expected return. That's your output that you want to maximize. Here are your decision variable, stock A and stock B. And here are your constraints. I have put the constraint here, the total less than equal to the maximum. Make sure that this is checked because this is, you don't want to have negative. You can't buy negative shares of a stock A or B, so you have to be non-negative values. And from this menu, make sure that you have selected the simple XLP method, which is the methodology that is used to solve linear programming problems. And you hit OK, and then it's going to solve it for you. And it's going to generate the problem for you, the optimal solution for you. So let me actually, so right now, if you see here, there is 0. We don't have any optimal solution here. If I click OK, it says that this is the objective value. Here's the buy, solve, and it solved the problem. So right now you see that from 0 it turns to 100. This is the optimal solution. So your best investment plan is to buy 100 stocks of A and 100 stocks of B, and your expected rate of return will be $78 after a year. Also, on the right side, you see that there are some reports that you can actually ask to print out for you. You have the answer report, the sensitivity and limits. We have covered the answers, so I'm not going to go to answer. Answer is not that much important here. So this is the answer report, which is kind of summary of what we had there. So this is the variable cell, which is the optimal solution. The original value is $100. The final value 100. So if I had started from 0, this would be your original value. This is your optimal solution. And the values are integer. The integrality, it says continuous. We assume that they are continuous here. And in the down below table, you see the constraints. Okay, so the constraints, you have 3 constraints for the how much you can the maximum that you can invest on a stock A, stock B, and a stock and the total. So for this constraint, you see this table, and the sell value is 400, 600, and 1,000. Okay, so these are not the right-hand side. The right-hand side was 700 for a stock A, 600 for a stock B, and 1,000 for stock for the total. But here you see that for a stock A actually is less than 700 limit that you set. For a stock B is actually equal to, and you have spent all your budget. Okay, and also in the last columns you see that for the status says non-binding. That means that stock A is not the constraint is not on the optimal solution, which is the corner point. If you remember the corner point, so the corner point is just the intersection of 2 constraints in the graphical method that we went over. So this is not binding, but the 2 others are binding. The other table that this can actually report that can produce for you, it's sensitivity report, and that's actually very important and a more useful actually report. So you see it here. You have 2 tables here, one for variable cells. So for variable cells, you only have 2 variables, stock A and stock B. The final value or optimal value is 100. So and the next column, it says reduce cost. What does reduce cost mean? It actually means that if you look at the objective coefficient that's actually the coefficient of objective function that we have here. So it was 6% multiplied by 4, which is 24%, 0.24 for A, and 9% multiplied by 6, that's 54% for B. So you see the coefficient here, but you see the allowable increase and allowable decrease. What does this mean? This means that the current solution that you have, which is 100 stock A, 100 stock B, and your optimal solution. This means that okay, if the coefficient of these stocks changes by within this range, your optimal solution would not change. That means that you will still have your optimal solution would be 100 of stock A and 100 of stock B. Okay. So by an increase of 12% and a decrease of 24%. So right now the coefficient is 24%. If you increase it by 12%, that means that by if you change it to 0.36, you still would have 100 as an optimal solution. Okay, so let's do that. Let's change the 0.24 to 36. Okay, so I'm gonna change this to 36 here. So right now it's not solved. Let's solve this first. Here. Okay, so that's 24 and 54 right now. You see here, multiplication of this. So we would have to have a cell for this to be able to change it, right? So this is difficult in this setting to do it. Anyway, let me go back here. Okay, so if you right now the multiplication of the rate of return by its price was 24%. If you decrease it to 12%, it still would be 100, your optimal solution. Okay, let me see how I can change it. Okay, 4 multiplied by 6%, that would be 24. So 3 multiplied by that would be 18%. 18%. 12% increase. So if I go to level 36, 36 36. So if I change this to $5, our optimal solution should not change. Data return. So as you see here, will actually change. 5 multiplied by 6, that's 30. Right, so I'm going to go back. Right, so this is difficult to do in this setting, but this is what it means. Okay, this is a very important table because the model that we had here, the price of share price per share for stocks and also rate of return, they could not be that fixed. They could change, for example. So you might not be sure about the price or about the rate of return. So this actually table can help you to see what would happen if the price would change, or for example, the rate of return, or in general, the coefficient of your decision variable in the objective function would change. So here right now they are 0.24. The allowable increase, it means that if it increased by 0.12, that means that 30.36%. Then your objective, your decision variable optimal solution would not change. Or if it decreased by 24%, it would not change either. For the stock B, your other optimal solution, the objective coefficient right now is 0.54. If you can actually increase it to infinity, and it still would be, it doesn't matter, and you cannot actually buy more of B, because if you look at the model, you see that one of your constraints was you cannot invest more than $600 on a stock B, and you already are spending $600 on a stock B. So it doesn't matter how much lucrative a stock B would be. For example, if the rate of return instead of 9% would be 90%, because of this constraint that you have set, it wouldn't change the your optimal solution. Your optimal solution would be still 100 shares of a stock B. And the allowable decrease would be 18%. So that means that if you decrease it by 18%, the coefficient right now from 0.54, if you subtract it by 18, that would be, if you change it by 18%, decrease it by 15%, by 18%, your optimal solution it still would be 100 of a stock B. Okay, so that's for your decision variable. In the next constraint, you see a table, another table here. That's for each actually constraint that we have here. And you have some information here. So these are the final values: $400 for stock A, and the right-hand side actually was 700. So as you see here, the constraint for stock A is not binding. Okay. For stock B, we are exactly the left-hand side is 600, the right-hand side is 600. So that's a binding constraint. The budget constraint, we have $1,000 budget. The amount you spend is actually 1,000. So you the third constraint is also binding. So this is also show you the allowable increase and decrease on the right-hand side, so that it wouldn't change your optimal solution. That means that, okay, so if you decrease your budget by 300 or 400 for stock B, it still wouldn't change. And also this is for allowable decrease. Right? So these tables actually are helpful when you make a decision and you find your optimal solution, but still you're not sure about, for example, what would it change, or for what if scenarios, that what if, for example, the coefficient of one of your decision variable changes, either decreases or increases. You could actually decrease or increase your implement that change in the model and then solve it. But this sensitivity table that actually can help you to kind of forego that without doing the analysis. You can actually foretell and predict, okay, whether your optimal solution would change or not. Okay, so this is what this table is about. If I can get this back here. Right. Any question? So we covered this sensitivity report here, constraint table. So, all right. So the model that I run, it actually produced for you the optimal solution. But you could actually have other scenarios. The other two possible scenarios are you're going to get an error would say that an error message that would say that, okay, your model is infeasible, or the other error message that you could get is that your model is not convergent. Okay, so what does this mean? Let me go back to the model and show you an example of that. Right. So this, when we solve this using solver, it says that, run it again. So you get this message. Solver found a solution. All constraint optimally conditions are satisfied. Okay? Solver found a solution, all constraint. That means that it found an optimal solution for your problem. Okay, so the other two possibilities is that your model is not actually feasible. That means that there is no solution for the problem such that all the constraints are satisfied. Okay, so how would that happen? For example, if I say that I think I changed this from 4 to 6. So you see that the 100 doesn't change. So I was kind of random about actually the weather rule. If I say let me actually delete this and add other constraints individually. So I would say that this cell should be less than this cell. This cell less than, which is here, less than this cell. Instead of less than, I'm going to say greater than. Okay, so I change one of the constraints. I want to show you an example or a scenario where you wouldn't get a feasible solution. So I change one of the constraints. I'm going to add the other constraint as they are. So this less than this value. I'm going to add the other constraint, this less than this value. So I change one of the constraints from less than equal to greater than equal to. Okay. So everything is stayed the same. If I click OK or solve here, still found a solution. Okay, so give me a moment here. I want to find a scenario where you wouldn't get the one solution here. Less than change. So I'm going to change this to this greater than this. Okay, this is how you get what you get here. The message. Okay, so this is what I did. I changed the right-hand side for the stock A constraint. Right now, it should be less than 700, but I just changed it just to matter of showing you a scenario which we wouldn't get a feasible solution. I changed that into your left-hand side should be greater than 1200. Okay, your budget is 1000. That means that, okay, so this problem asks you, you cannot spend $1,000 on investment But also it says you should buy at least $1,200 dollar value of a stock. So it doesn't make sense, right? So that's why when I hit solve, it says solver could not find a feasible solution. The solver cannot find a point for which all constraints are satisfied. Right? So that's one message that you can get. And another message is that you would get your problem or your model is not converging. That means, what does it mean? It means that your profit, for example, is infinite. Okay, so that also, of course, that's actually an error in your model. Or it would say, if it's a minimization problem, it would say, okay, your for example, objective value is negative infinity. Okay, so that shows that there is a constraint or some information wrong in your problem, right? So if you face such an issue, it could be that you have forgot to add the non-negativity constraint, which just checking the constraint box, or if it's you have actually kind of misplaced your constraint symbol. For example, instead of enforcing a less than equal to constraint, you have put an greater than equal to constraint. Okay, so just remember that if you're dealing with a problem like that, you probably have written your model wrong. All right. So when solver cannot find a feasible solution, you saw an example of that. Feasibility can be harder than the other one to fix. So you could check for the less than equal to or greater than your constraint actually sign. That there could be a problem with that. Or it could be that your right-hand side is actually kind of missing some digit. For example, instead of putting 1,000, you have put like 100 or some other values, right? So you have to check your constraint as well. But generally, finding what is wrong or debugging your problem when you get the message that your problem is infeasible, that's generally difficult. Right? The other message that you could get that your model is not converging or does not converge. That means that it's what it's called, we call unbounded, but that means that your model is going to go to infinity. So that means that your constraints are not able to enforce the problem in a kind of a limited actually space, right? So some of your decision variable could go to infinity. Okay? So for example, you could buy infinite number of stock A, which is ridiculous, right? So that means that, okay, you have to check for your constraints, or you might have forgot to, instead of clicking on the minimization problem, you have to click on the maximization problem, or vice versa. Okay, so now we want to do some sensitivity analysis using the solver table. What is solver table? I have actually put some information in Island for you to see that. But if this is like an add-in tool that Albert, Dr. Albert has actually invented, and he has made it available for free. You can actually look it up online, and I have put actually you see actually the link here. This is the hyperlink that you can. If for any reason, if this doesn't work, just Google for solver table add-in Excel, and it's going to get you some information. Probably the first or the second actually web page or address. That's your place to go. You're going to go there, and you can find information about a document which have already uploaded on Iron. So you can see that one, which is going to give you a description of what the solver table is called. Solver table help. I also have actually put the download link in Ireland too, so you can find it there too. right? And this add-in, it could be difficult for you to install it. It's a little bit tricky, but I'm going to try my best to do that. I already have it here. So let me see if I can show you how you can do that. So what you will download, it's going to be an Excel file. It's called solver table. Okay? You could click on it, double click on it, and it's going to open and it's going to work. If it doesn't work, probably if you have a Mac, you could have a problem with that, but there are resolution to that if you just read the solver table help. If you're using Windows, there is likely that it's going to work. The other way that you can get this work after downloading the file that I have done it here, let me share my Excel file with you before I try to show you how to do it. So this is my Excel file. If you don't have I already have the solver table here. If you don't have the developer tab here, you can actually go ahead from the options here and try to install the developer tab, or you can click on the ribbon here and says customize the ribbon. Okay, and then make sure that the developer here is checked. Okay, so make sure that this is checked and hit OK. And then you're going to have a developer tab, the developer actually ribbon here. Okay, developer tab here. In the developer tab, you're going to see the add-ins here. Okay, so click on the Excel add-ins. It's going to bring up this menu for you. Right, you can see actually the solver add-in here and the analysis toolpack that we already have here. I already have the solver table, so that's why you see it here. But if you don't have, you're not going to see this one because you haven't installed it. Okay, so after you got this menu, you're going to hit browse. Okay, hit the browse button, and here go ahead and find the downloaded Excel file, the whatever it was called. It was called the solver table. Okay, so find the solver table here. Solver table. Then hit OK. I already have done it, so I'm not going to do it again. And then it's going to bring it up here. Then you check this item, solver table here, and hit OK. And then you're going to have this table appearing in your ribbon. Okay. And it is very simple. It just has these four items. Okay, run solver table help, and these two. Don't worry about that. Okay. So we're going to use this solver table to do some one-way, two-way data table analysis that we used to do in previous lectures. Okay, remember that we have to do some one-way table, two-way table analysis. So you could actually do one-way and two-way analysis on an optimization model. So that's what it would think about the solver table. Right, so there is also one thing that I had to do, I remember, for my Excel to get this to work. If you get this error, it says this file type is not supported in protected view. Okay, so if you download the solver table Excel file, you double click on it, try to open it, and it says this file type is not supported in protected view. Or if you install it in the ribbon, and again, next time that you run it, Excel, it says, okay, this type of file is not supported in protected view. This is what I did in Windows, and it worked. Okay, so I'll right click on the file, the Excel file solver table, and I went to the properties, its properties. Okay, let me show you right here. Okay, so this is the solver table Excel file. I right click on it and it gives me this menu here. I go to the properties, and in the properties, you cannot see here because I've already done it, but you're going to see another actually checkbox here that would say unblocked. Okay, click that one, check the unblocked one, hit OK, and you would not have any problem anymore. Should not have any problem. This is how it works for me. Again, if you have still after you try to install these add-ins, we still have problem, try to go to the solver table help and see if you can find any help over there. Otherwise, you just have to follow the course. You know, you could do this analysis by just manually, but you have to do it multiple times. It's going to be a little bit tedious, but it's not that that's the only data. So basically, data table is just repeating some analysis and computation with different values, with different inputs. For example, with the different interest rate. Okay? Any question? All right, so one-way solver table. So we want to see an example of one-way solver table to do a one-way analysis on an optimization problem. So first of all, you want to see how will the optimal solution or optimal objective value or anything else would change by changing an input. For example, the price of an stock or the rate of return of an stock, or for example, your budget. Okay. So solver give you this option that you can do. Suppose that we want to do this, okay? So we want to see how does the optimal total return changes as the investment budget grows from say 500 to 1500. So this is how you would do it. Let me open a GLP Excel file. Now I'm going to share with you. Oh, this is the close it. I have to reopen it. I close it because I don't want the changes that I made to be saved. Now let me. This is the investment LP problem. You see the problem here. And we want to do a one-way analysis. So we want to see, okay, what if our budget changes from 500 to 1500 by say $100 increment. And we want to see how would that change in our optimal solution. That means our investment return, rate of return, and also our decision variable. That means how much of the stock A and stock B we buy. Okay? So we want to see the changes in the input, which is the budget for 500 from range of 500 up to $1,500 by increment of $100 on the how much we would make and also how much stock A and stock B we buy. Okay, so I go to this. So you have this sheet. You have to be in this sheet. The sheet have to be active. The sheet that your model, the LP model, is in. It has to be active sheet. Then you go to the solver tab, and then run solver table. Okay? It says you should have an existing solver model. That means that okay, your model you have to have an Excel model here. You have to have already solved it to have an active one. That means it has to be active. Hit OK here, then it's gonna bring you this table. You see this? Do you see this menu here? Right. So it says whether you want a one-way table or two-way table. So I'm gonna go with one-way because I want to only change your budget. Okay, there is one input that I want to change. So I hit OK, and it's gonna bring me another menu here. This is the menu. Right. So this is the input cell that you want to change, which is the budget. Okay, so I'm going to change the budget here. So I want to change the budget. I'm going to say budget. Okay, and this is my range. I want to say, okay, so it starts from 500 to 1500 by an increment of $100. And what are the output that I want to see? forget about these two. This is another way that you could actually implement these changes. What I want to see is, let me get rid of these. I want to see the changes on my optimal solution decision. That's how many of the stock A and stock B I should buy, and also my rate of return. So I'm going to hold the control key down and then click here, which is my expected return or rate of return. Okay, so this is how I did it. Right? I grab these two cells, which are my objective solution, and then I hold the control key on Windows down, and then I selected this expected return or our output. Right, and then if you hit OK, it's going to create for you a table. Right, so it's created the STS3, which is I already have now. Right, so it says one-way analysis for solver model in model worksheet. The budget cell values alongside. This is the budget. It goes from $500 to $1,500 by increments of $100. And in the next three columns, you see the changes in your output. The first output was this: how many shares to buy from a stock A, how many shares to buy from a stock B, and the last column is your rate of return. So, for example, if your budget is $500, your optimal solution is to not buy any stock A at all and just buy 83.3 stock B, and your rate of return would be $45. If you invest, if your budget is, for example, $700, the optimal solution is to invest 25 stock A, to purchase 25 stock A and 100 stock B, and your optimal rate of return is $60. So you see all this information here. And you see actually another part of information here. You see this graph and this column here. It says data for chart. This is actually, you can actually change this. This is automatic. You can actually plot your whatever you want the output to be, because right now you have three outputs. You have the stock A, number of stock A, number of stock B, and your rate of return. And you can actually graph these changes based on your budget, changes in budget. So because they are three and you have two dimensions, you can only pick one of these. For example, I want to pick or plot the changes in budget and the impact that it has on expected rate of return. So here from this three menu that I have, three options that I have, I'm going to pick the expected rate of return and click on it, and it automatically going to plot for me the expected rate of return based on my budget. Okay. So my budget goes from $500 to $1,500 on x-axis, and on y-axis is my rate of return. So as you see here, my rate of return increases like linearly from $500 to about $1,300, and from there it's going to keep just being flat. You could try other output, for example, the amount of stock A. So this is the amount of stock A. If your budget is something between $500 and $600, on the y-axis is the number of stock A to buy. That's your 0. And then from when your budget is 600 up to 1,300, your number of stock is going to increase. Okay? And after that, it's going to become flat. You can see it for stock B too. Just for stock B. So for stock B is just very simple. It's from 500 to 600. You increase your budget, you're going to have an increase from 83.3 to 100, and from there it's just going to keep being flat, because you have a limit, you have a constraint on a stock B, and that's you cannot purchase more than, invest more than $600 in stock B. But because of that, even if you increase your budget, your problem, you cannot actually increase your number of purchase of a stock B. Okay? So this is a one-way analysis, data analysis using the solver table. If you wanted to do it with without this actually, so you kind of have to rerun this problem with this number of which are about 10, probably 15, 10. It's about 10. So you have to rerun the experiment like 10 times and then keep everything or save everything, store everything in one place to be able to have a plot or have this table. Okay, but this actually add in, it just, as you saw it, very quickly. You could also do it other analysis. For example, suppose that I want to do a one-way table analysis. Let me get rid of these. So suppose that I want to see what if my my stock price changes. For example, a stock A right now is $4. I want to see stock A price. I want to see whether how much it would change if it changes from 1 to say 10 by increment of 1. And I want to see the changes on these two guys, the number of A and number of B, and my output. I'm going to hit OK here and do a little bit computation and it runs it for you right here. Right? So you see the price for stock A here from $1 to $10 increment of $1, and here's shares to buy from a stock A, shares to buy from a stock B. It doesn't change, it's 100, and your expected rate of return. Okay. So I'm going to not save this. I'm going to close it and then open it again. Any question? So that was a one-way analysis using the solver table. You could also do two-way analysis, which I'm going to show you how. So two-way data table analysis. If you remember, in the two-way table analysis, you had two inputs. You wanted to have them change from like within a range, and the other also within a range. You have it like one in column and other one in rows, and then you could only see the impact of these changes on one output. Okay, so it's not like the one-way table that you could have them multiple. So suppose that you want to see how does the optimal strategy and total return changes as the maximum value on those A and B changes. So the input cell would be stock A max, cell 2 would be stock B max, and the output would be the decision variable cells for the objective. Or you could do it, for example, for price or the rate of return or your right-hand side constraint. Anyway, for any two inputs, you could actually run the two analysis, and it's not that difficult. So this is how would you do it for two-way data table. You run the solver table. I'm going to give you again this menu here. You're going to check the two-way table, hit OK, and it's going to give you this table. Right? So now you have two input cells. It could be, for example, your stock A price and a stock B price, then you're going to name it here, and the minimum value, the maximum value, the increment, the minimum value here, the maximum value here, increment. The output said it has to be 1, and then it's going to produce it for you. You could actually run more than that. It's actually, because this is like Excel adding, you could put more than one output. This is not Excel itself, it's an add-on Excel. So it has that capability of doing two-way analysis on two actually inputs on multiple outputs. Okay, so we covered that one too. Any question? All right, so if you don't have any other question, we're gonna move on to another topic. So what we did so far was solving an optimization problem, which is a maximization problem. So now we're gonna do another problem, which is a minimization problem. Okay, so this is a minimization problem. It's called the diet problem or a small diet problem, and it's a downsized version of an original problem which was solved by, or actually presented by, George Vedantic, the mathematician that actually came up and invented the simplex algorithm, which we talked about it last week. Okay, so that's it has less fewer number of decision variable and fewer constraints, but the original problem it is the same. It has just more. The dimension is just higher. Okay, so it's a blended type of LP problem. It's a minimization problem, not maximization problem. So it's going to be different. You are, for example, minimizing costs, or you're minimizing the number of staff, or whatever for minimization problem. Here we are minimizing the cost of our diet. Again, it's a simplified of another problem. We only have 4 decision variable or 4 type of food. We have, for example, milk, tuna, and bread and spinach. And our nutrition constraints is the only 4 of them. Vitamin A, we're concerned about vitamin A supplement or limits vitamin C, vitamin D, and iron. Okay. We have the what do we have? We have our inputs are the cost per unit of food, the amount of nutrition per ounce of food for each food for the 4 food that we have, and the minimum daily requirement because we want to have a healthy diet. Okay? So this is what we have. And by the way, you can actually find the original paper for the diet problem here. So this is how I would set it up in a mathematical format. Okay, so here on the first row here, you see my optimization formula or objective function. It's a cost because we are minimizing the cost of our diet. This is what we want to do. We want to come up with a diet plan so that it would meet our nutrition requirement per day or per month, whatever, and per day. And then also our choices in such a way that the cost is minimal. Okay, so with minimal cost, we are meeting our nutrition. So for milk, for example, this is the per ounce of milk. It's going to be 6 cents. For tuna is 50 cents. It's more expensive. Bread is 13 cents. The spinach is 35 cents. And milk, tuna, and bread, we're going to show them by, these are going to be our decision variable. How much milk, how much tuna and bread and spinach we have. So we're going to have 4 decision variable. I'm going to show milk by M. I'm going to show tuna by T. Show bread by B, and show spinach by S. Okay, and we're going to have 4 constraints on our nutrition requirements. So for vitamin B, our requirement is to have at least 5,000 international units. IU stands for international. So these units are either mg, the milligram, or international. For vitamin C, we want to have at least 55 milligram per day. For vitamin D, we want to make sure that we get at least 800 international units. So 800 or more. Okay? So these are all greater than equal to. Okay. And for iron, we want to make sure that we get at least 12 milligram. So 12 milligram or more. Okay. So in the left side, you see the constraint coefficient. Okay. So milk has 50 units of vitamin A. Okay. Tuna has 14.81 international units of vitamin A. Bread doesn't have vitamin A, this type of bread. And spinach has 2,125. Pretty impressive, very, very nutritious. For vitamin C, milk has 30.31 milligram of vitamin C. For tuna has 28.28 milligram of vitamin C. Bread doesn't have vitamin C. Spinach has 4.44 milligram of vitamin C. For vitamin D, milk has 12.5 50 international unit. Tuna has 37.50, and etc. etc. So I'm not going to read through all of this, but this is how I would set up my model in here mathematically. But I'm going to show you how we can set it up in Excel too. Okay. All right. So what is our decision variable? Ounces of milk, tuna, bread, and spinach. The 4 food that we have, we want to see, okay, what is our best diet? How much milk, how much tuna, how much bread and spinach we should buy so that our nutrition requirements are met. What is the objective function? Minimizing the total cost of this diet plan. Okay, and these are our constraints. So we have 1, 2, 3, 4 constraints for diet or nutrition constraints, and we have the non-negativity constraint because you cannot purchase negative number of bread or negative amount of milk. Okay? So we make sure that you have the non-negative constraints here. And again, we are this is a minimization problem. Okay? Our previous problem was maximization problem. So I'm gonna stop sharing this one. I'm gonna actually create our model actually this problem. Okay. So because I want to follow the format that we have, what you can do is either input merge the format, or you can actually open up the style that I already showed you how. So I'm gonna open up, for example, my style here. This is my style. I'm gonna open up here. Right. So here, if you go to the style, can merge a style.
Professor,
Professor.
there's nothing on the screen.
Oh, it doesn't show anything?
No.
Okay. All right. So my style file is open now. If you look at the cell style here, because I have opened that and I merged it, you can see the format that we have. Okay, output is gray, the my input is blue, decision variable is red, and calculation is just black. Okay. So this is, you see this Excel file? This is the empty Excel file. Right.
Yes.
So first of all, I'm gonna rename this sheet as my model. So it's just model. And let me make this bigger. Here I'm gonna say simple diet LP. I don't need the so I'm going to close the model style. All right. Then we put the inputs. Okay, so these are going to be our inputs here. You don't have to put inputs here because you already know these are inputs. Because we're going to make them. Okay, so for example, we have the cost per ounce for each food. Okay, so cost per ounce. And here we had it for milk. We had it for tuna. We had bread. And we had a spinach. I'm gonna make this align right. And align in the middle center. So cost per ounce for milk was 0.6 cents. Okay, so it was 0.46. For tuna, it was 50 cents. So it was. For bread, it was 13 cents. And a spinach was 35 cents. These are my input. Decision variable. So the decision variable is just going to be milk, etc., etc. So I'm gonna just copy these here, and the values is going to be here. I'm gonna center these, and these are going to be my values. So right now, if you leave it empty, that means it's 0. I'm gonna change it to, for example, other values, 1 and 1, just for a start. Because when you run the solver, it's gonna automatically compute the original values. But if you leave it 0, then your optimization, your objective value is going to go to 0. All right. Says amount in diet. Okay, so good so far. Now we need to go to the next component of our model, which is our constraints. So I'm going to write our constraint. So for our constraint, we had the nutritions, vitamin A, for example. We had vitamin A. We had vitamin D, C, vitamin D, and iron. Okay. I'm gonna make them right align, and then here I'm going to do my constraints. Right. So before I move on, because we got to the 7:43, almost 7:45, I'm gonna just head for the break. If you want to make a break, take a break. You can take a break. Then we're gonna come back after the break, 15-minute break. We're gonna continue our. So let me actually pause here and also pause here, and then. All right, welcome back, everyone. So let's get back to our modeling. We're solving a daily diet problem. Here I'm sharing the screen here. Okay. Right, so we listed our inputs. You don't have to actually exactly copy the way that I do it, but we need to have like a style or format that we have. Right, so let's go ahead for constraint. We have for constraint for the daily dosage of vitamins and nutritions, vitamin A, B, A, C, and D, and iron. And here, because each one of these foods is going to have their own daily diet, I'm going to put them on the column. Okay. So vitamin A, these are going to be our inputs for this. Okay. I have to actually put them here for each. Milk and vitamin A, it has 50 international units. Tuna has 14.81 international unit of vitamin A. Going to centralize center, alignment center. And bread has 0. The spinach has 21.25. Vitamin C, 30.31 milligram. Vitamin C for milk. For tuna, it has 2.8 vitamin C. Bread has 0, and a spinach has 4.44 milligram of vitamin C. Milk has 12.50 international units of vitamin D. Tuna has 37.5. Bread has 0 vitamin D. And spinach has 25. For iron, milk is 0.22 milligram. And tuna is 0.44. Bread has 0.81, and spinach has 0.50. Okay. And here I'm going to put the summation of consumed one for each one of these. So for vitamin A, you're going to consume based on how many milk you have, how much milk you have, multiplied by the amount of nutrition has for vitamin A, then it's going to be plus how much tuna you have multiplied by how much vitamin A it has. You have to have this sort of computation here. All right, so to simplify our computation, I'm going to first of all go and use the range names here. So I'm going to put this as cost per ounce for modeling purposes. So I'm going to go to formulas here, create from selection. This is left column, that's right. This is amount in diet. It's going to be also here. All right. And now, instead of doing this multiplication, milk multiplied by its dietary value plus tuna multiplied by its dietary value plus bread multiplied by its dietary value plus spinach multiplied by its dietary value. So instead of doing this tedious work here, what I can do is I can use the sum product. Okay, sum product. So sum product is going to get two arrays. So I'm going to get this array. I want to multiply it by this array. Close it, hit enter, and automatically it's going to apply. Okay, it's called sum product. Sum product. Let's have our model from whatever. Right, and the good thing is about this is actually extendable and copyable. I can just, instead of computing for others, I can compute it. I can drag it down and it will be computed for others. Okay, because we gave this a name, amount in diet. See, it's amount in diet for this and this. So when I go to the next row, the amount in diet is going to be fixed. So it's going to be, it doesn't move to the next row. But the constraints one, the dietary value is going to move to the next. So that's why I can actually drag it down. It's copyable. It makes our computation so much easier. Okay. So this is our consume one, and these are actually inputs. So I'm going to give this also the input format. Okay. All right. So now we have to write our constraint here. If you look at our model here, the vitamin A has to be greater than 5,000 MDR. Okay. So here, I have to write the type of constraint. So you can write this greater than or equal to sign like this, or you can actually use the symbols here. So insert symbols, greater than equal to, insert, close, and then now I can just copy and paste it for the rest of them, because all of these constraints, if you remember, have greater than equality. Okay, so we wanted to have at least 5,000 international units of vitamin A, at least 75 milligram of vitamin C, and at least 800 international units of vitamin D, and 12 milligram at least of iron. So that means greater than equal to 12, greater than equal to 800. Okay? So all of these values are greater. Okay. So now I'm going to use the meal daily requirement. This is meal daily requirement or nutrition daily requirements. So these are going to be our inputs here. Okay, so for vitamin A, we know that we wanted to have at least 5,000 international units. Okay? For vitamin C, we wanted to have 75. And for vitamin D, we wanted to have 800. And for iron, we wanted to have 12. Good. So this is international unit. This is milligram. This is international unit. This is milligram. Okay. All right. So here I'm going to write my my objective function. Okay. So here I'm going to say the total cost. We are minimizing total cost, and this is going to be objective function. So I'm going to measure this, and under cost, I'm going to write the constraint. So the constraint is how much milk is cost per unit multiplied by how much milk you buy, plus how much the price of tuna per unit multiplied by how much you buy, plus the amount of how much price, the price of bread multiplied by how much bread, plus the price of the spinach multiplied by, right? So this is again sum product. Instead of doing this TDA computation, I'm going to use the sum product, and I'm going to select these cells, then put the comma here and select these cells, and hit OK. Look at here, it has two arrays here: the cost per ounce, which is the prices, and the other one is the amount in diet, which is how much we purchased and use. And this value is actually our output. Okay, so I'm going to use the output cell for it, and I'm going to actually name it. So top row is the Excel actually is a smart. It can understand when you select a couple of cells, it can understand the label, where the label is located, the numbers and the values and the non-values. So the top row is the label. I'm going to hit OK. So now I have this value, total cost, and we had this and this and this way. So we can actually see our name tags here. Name manager, if you click on this, you're going to see this. You have the amount in diet, you have cost per ounce and total cost. Okay. The other thing that we wanted to select is the MDRs, and the consumed one, because I want to use it in the model. So create consumed and also MDR. See, if you look at the name manager again, you're going to see all the 5 name range that I have used. Okay? It is actually a good practice to put your range names on the sheet that you use it, so that if you come back to it, you know what range names you have used. Ranges. So here I'm can go to the formulas, use in formula, and then paste names. Okay, so I'm gonna click here and click paste names, paste list, and it listed all of the okay. So it's amount to diet, MDR, total cost, etc., etc. Right. So this is also a good thing to have. Right. So we should be good. I'm gonna get rid of one of the rows to make this closer. Everything should be close to each other. That's a good practice. That's a good modeling practice. I'm gonna also get this, make it neater. All right, good. So we are ready to solve the problem. Okay, so we are minimizing the total cost to meet this requirement right now. So right now, if you look here, the 111 unit of these foods, the cost is $1.04, but it's not a feasible solution. Why? Because our constraints and limits of daily nutrition are not met. For example, for for vitamin C, you only get 5 milligram, while we need 75. Also for vitamin D, we need 800 and we get 75. For iron, we need 12, and right now we have 1.97. So this solution of 111, although the cost is $1, it's very cheap, but it's not feasible. It does not meet our requirement. Right. So I'm gonna go to solve this problem to optimality. Go to the data tab, solver, and here set objective. So this is going to be your output. Okay, this is the output. This is the total cost. Okay, this is a minimization problem. So make sure that you click on the minimization. Otherwise, the default is maximization. Okay, so I'm going to hit our minimization. Then by changing value cells, this is our decision value. So I'm going to select this range of dietary foods. What food you want to buy, or how much from each. Okay. Now, the next is to add the constraints. Okay, so you could add the constraints one by one. For example, the consumed vitamin A should be greater than 5,000. But because all of these are 5,000 are greater than, the inequality sign is greater than, they are also the same. I can, instead of like putting one by one, I can actually add them by one list. Okay, so instead of like putting the vitamin A greater than 5,000, add, and then vitamin C greater than 75, add, and then consume vitamin D greater than 800, add, and then consume iron greater than 12, and okay. Instead of adding these 4 constraints here, what I could do is I can add them at once, because all of them share the same inequality sign, and that's less greater than equal to. Okay, so I'm gonna pick all of these 4 constraints, make sure that this is greater than, and on the right side I'm gonna pick this guys and hit OK. Now you see that I have total cost here, minimizing the total cost by changing variables of amount of in diet, and the constraint is the consumed amount of diet or nutrition should be greater than equal to our requirements, daily requirements. So we are done with the model. Now the rest of this is you have to make sure that this is selected, because you cannot have a non-negative value of any diet. For example, you cannot buy and consume -2 of bread, right? So you have to make sure that this is selected. And then for solver, selecting a solver, make sure that you select the simplex LP, and everything is good. Now look what we have here. I have 1 milk, 1 unit of milk, 1 unit of tuna, 1 unit of bread, 1 unit of spinach, which is not a feasible solution. So when I hit OK, it's going to compute and find the optimal solution. It's going to give you the optimal value of your decision variable and also the total cost. It's going to give you this next window. I'm going to ask it to produce the sensitivity and the answer report. All right, so it actually works. These are your optimal solution. So it says that you have to purchase 35.12 units of milk, gallon or whatever it is, no tuna, no bread, 14.44 of spinach, whatever the unit is, and your total cost would be $7.16. I'm going to make this actually a little bit neater. Same as these guys. So I'm going to reduce the decimal points and see what happens. So with this daily diet of 35.12 of milk, no bread, no tuna, and 14.44 units of spinach, you get, instead of 5,000, you get actually 32,000 of vitamin A, exactly 75 milligram of vitamin C that you required, exactly 800 international units of vitamin D that you required, and you get about 14.95 milligram of iron, which is a little bit greater than you require. Okay. And also it produced for you 2 other sheets here. Let's go to the answer report sheet. So the answer report sheet, it doesn't give you much information. It's not really that important. It produces for you 3 tables here. The first one is the objective cell. So it says the total cost is your objective function, and the original value was 1, and the final value is 7.16 something. The next table is the variable cells. So that's your milk, whatever the daily diet. And the original value, I gave it 111. The final value is 35. I'm going to make this actually more readable here. So let's just do the meter. Right. 35, almost 35 units of milk, no bread, no tuna, and 14.44. And it says the entity type, the constraint type, or the value type is continuous. And then the last table is the constraint table. So here it gives you information for each constraint, which is the daily diet for vitamin A, vitamin D, vitamin C, D, and iron. It gives you the cell value here. So I'm going to make this also. Okay. It gives you the formula, the constraint symbol, and also it says that non-binding and binding constraint also give you the slack. Okay. So that make this. So for example, for vitamin A constraint and the iron constraint, it says it's not binding. What does it mean? It means that if you remember from the graphical method that we had last week, your optimal solution actually is going to be a corner point. The corner point is going to happen on the intersection of 2 constraints, okay? 2 constraints. If that constraint is one of these constraints, that's going to be binding constraint. So if it says binding, that means that the constraint that you're talking about, that includes the corner point, which is the optimal solution. So the optimal solution is not on the vitamin A constraint, nor is in the iron constraint. That means that if you look at it, you see that the left-hand side and the right-hand side, they are actually way outside of the requirement. They are not equal, okay? So the left-hand side for vitamin A is not equal to 5,000, the right-hand side. The left-hand side of iron constraint is not equal to the right-hand side, which is 12. But for the other 2, vitamin C and vitamin D, the left-hand side, 75 and 800, is exactly equal to the right-hand side, which is 705 and 800, okay? So this means that these 2 constraints, C and D, are actually binding. That means they include the optimal solution because they are exactly equal. And a slack is just how much is your usage is off from the right-hand side. So if you see for the vitamin C, vitamin A, your requirement is 5,000, at least 5,000, but your usage is 32,000. Okay, so it's about 27,000. You have 27,000 in slack. You don't have any slack for vitamin C and D because the daily usage that required is exactly how much you consume. For iron, you require 12, and you get 14.9. So you have a slack about 2.9. So 2.95 exactly. Right. So this is about what you can understand from this data in the answer report. You get more information from the sensitivity report. Okay, so in sensitivity report, you get 2 tables, one for variable cells and one for constraints. Let's focus on the constraints, the variable cells right now. So I'm going to make these all neater. Shouldn't have included. So if you look at the values that you have 2 values that are infinite for computer right now. It's 10 to the power of 30. That's the biggest value that you can store in for this computer. So that's why this is practically infinite. So I'm gonna clean this up and reduce the number of decimals that I have here to 3. Here I'm going to do the same. Okay, so the final value you see for the amount for milk, for tuna, etc., etc. Then you have the what is called as reduced cost. I'm going to tell you what it is. For these are the objective function coefficient for each nutrition or for each food or variable. Okay, so for example, for milk, the objective coefficient is 0.06, which is 6 cents. That's how much it costs to buy a unit of milk. Okay. The allowable increase and the allowable decrease, those are the last two columns in this table. And these are going to tell you how much is this range of coefficient for this specific decision variable, that if you change the coefficient within this range, your optimal solution is not going to change. Your optimal solution, by optimal solution, I means your usage or your purchase of the daily diet, for example, from milk. Okay? So if it says that from 0.06, if you right now is 0.06 or 6 cents, if you increase it by 108 cents or 10.8 cents, it's not going to change. Or if you decrease it by 0.3 cents, 3.6 cents, your your optimal solution is not going to change. That means that you're still going to have to purchase 35.12 units of milk. Okay? The same goes for the other variables. For example, for tuna and bread, right now, your optimal solution, it says that do not purchase this, do not consume bread and tuna. The coefficients are 0.5 and 13. That's 50 cents and 15 cents. So because you are not using any, and this is a minimization problem. So if you increase the cost, it doesn't change your optimal solution. That means that if these are the allowable increase in the coefficient, and the coefficient is the cost. Okay, and this is a minimization problem. So when you increase the cost, it is actually logical to decrease that amount of that value variable because it is costly, right? But because we already not consuming any of these, so it doesn't matter. So that's why your upper level range for increasing the coefficient is infinity. That means that no matter how much you increase it, your optimal solution, which is 0, is not going to change. But it's going to change it for when you decrease it, because its cost. It says that if you decrease the coefficient right now for tuna, which is right now 50 cents, so if you decrease it by 35, almost 36 cents, okay, that's like 14. If you make it instead of 50 cents, if you decrease it to 40 cents, 1/4 cent, then your optimal solution is going to change, and that means that you're going to see tuna in your daily diet, optimal daily diet. Okay, so let me go back here. So right now it's 0.4. It says decrease it by about 36 cents. So that's like 14 cents. So I'm going to change for tuna from 15 to 0.14. And then I'm going to run the model. So look closely at your daily diet here, milk, tuna, bread, and also the total cost. So if I click solve, you see that tuna actually from 0 it becomes 10.51, right? So it actually so the optimal solution is to include tuna in your diet, and your diet changes. Okay, so I'm going to restore the original values here. I'm going to change this from. Okay. All right. For bread, the same. Right now, your optimal diet does not include any bread, but and the objective coefficient is 13 cents. That's how much it's cost you to purchase bread per unit. Because right now you're not have any bread, you're not consuming any bread. No matter how much you increase the coefficient or the cost of bread, it's not going to become your diet, optimal diet. But if you decrease it by 13 cents, then it's going to come back to your diet. Okay, so let's go back and do that. So right now, actually, the coefficient is 13 cents, and the allowable decrease is 13 cents. That means that if you make bread free, only that time you should include it in your diet. Okay, which is really telling for bread, poor bread. All right. And you see also for spinach. For spinach, the final value right now is 14.44. And the objective coefficient is, the cost of it is 35 cents. The allowable increase is almost 51 cents. That means that if you increase less than the price of spinach by less than 51 cents, then you're still gonna have 14.44 in your optimal diet. And if you decrease it by 23 cents, you're still gonna have the same 14.4 in your diet. So let me actually decrease it by 20 to less than 23. So by less than 23, that will be 22, for example. So that would be 32. So if I make it 32, exactly 32 for spinach. What is 13? 12. 12 solver. So spinach didn't change, although I changed the cost of it from 53, 52 something to 12.12 or 12 cents. It is still, the optimal solution is still recommend you to consume 14.44 cents or units of it. Back to 35. Right. So that's about this table. The reduced cost is how much should it change to actually turn into your diet or becomes part of your diet. Because the milk is already, the milk and spinach are already part of your diet, so that's why the reduced cost is 0. That means that if you reduce it by 0, it becomes part of your diet because it's already part of your diet. But for tuna and bread, which are not part of your diet, if you decrease the cost of bread or coefficient of bread by 0.3059, which is exactly the allowable decrease, it's going to be part of your diet. And also for bread, if you reduce the coefficient by 0.13, it becomes part of your diet. That's what the reduced cost means. Okay. Let's go to the next table. That's the constraint table. So you're going to have 4 constraints here for vitamin A consumption, vitamin C, and vitamin D, and iron consumption. You're going to see the final values or the optimal used values here. I'm gonna make this smaller. All right, so now it's easier to read them. Okay, so for vitamin A consumption or constraint, the final value was you consume with the diet that you have, which is this diet that you have. You're gonna have you will be taking 32,000, more than 32,000 vitamin A international units. I'm gonna talk about shadow price later. This is the right-hand side, so your consumption is greater than your right-hand side. The allowable increase and decrease, this is how much is it. That means that if you change the right-hand side, the right-hand side value, these are the values that allowable values for right-hand side values. Okay? So if you increase it by 27,000, you're still going to be fine. Your optimal solution is not going to change. Okay, so this is what it means. Allowable decrease, infinity, which is practically 5,000 instead of 5,000. You cannot have negative, but it's practically theoretically infinite. For vitamin C, your final value is 75, which is equal to your right-hand side, because this is a binding constraint. The allowable increase is 7.08. Okay? So that means that you can actually, if you increase the intake, the daily requirement intake of vitamin C, your optimal solution is still going to go up right now. This is our allowable decrease, and you also see it for the iron. All right, so that was it. We covered the sensitivity analysis for okay. So this is just a copy of the model that I already did, not this one that I do it right now. So what was different here? The situation was kind of opposite to the previous problem, because in the previous problem we were working on a maximization problem. So first of all, it was maximization problem. Second of all, our constraint was less than equal. So here we had actually a minimization problem. Our constraint was greater than equal to. Okay, now we wanted to do some analysis for this problem, some one-way table analysis here. So how does we want to see how does the optimal diet and its total cost changes as the MDR on vitamin D, the daily requirement on vitamin D increases from 800, which is to 1200. So right now is 800. You want to see what happened if it changes from 800 to 1200 by increment of 100. This is what I'm going to do. Let's go back to the model. Let's share that one and start shading this one. All right, so we see the model. We want to see the changes in vitamin D from 800. Right now is 800, and we want to see what will change in our consumption of milk and spinach and etc. other foods, and also our total cost if we change the daily requirement of vitamin D from 800 to 1200. So I'm going to go to solver table. I'm going to run it. So I'm doing this menu. This is a one-way analysis. I'm going to click one-way analysis. And this is the input cell. The input cell is this cell. Okay. This is the daily requirement of vitamin D. I want this to change. I'm going to say daily requirement the daily requirement. And the minimum value is 800. I want a maximum value is 1200. Can go with another value, increment of 100. And I don't worry about these two others because this is the same way, another way to change these changes. And the output, I want the output to be my decision variables. And so I'm going to hit Control, key down, then select this total cost. And I hit OK. Look at the number of sheets that you have here. You have 3 sheets here. If I hit OK, it's going to create another actually sheet here. STS number 1. So you see this table right here. So these are the daily requirement value along this side. So vitamin D requirement per day is going to range it, change it from 800 to 1200 by increment of 1. And then your output are going to be shown on these columns. For example, the amount in diet one, which is milk, the other one. So this is milk, tuna, and bread. This here. Milk, tuna, and bread. And that one is total cost. People kind of mess this up. So we're going to do this here. All right, so you see that if the daily usage or requirement for vitamin D changes from 800 to 1200, it's going to change your intake of milk. Okay? It's going to actually increase. Doesn't change the consumption of bread and tuna. It's still going to be 0. So that means that they are not important for produce or in terms of vitamin D requirement. The spinach also is going to change. Actually, it's going to decrease. We're going to consume less spinach and more milk. The total cost also is going to change, and it's going to actually increase. So by increasing your daily requirement for vitamin D, your spinach taking going to decrease, and your milk taking going to increase, and your cost is also going to increase. And here you can actually see the plot representation of this. So you have the daily usage requirement of vitamin D on the x-axis, and y-axis you have these 4 outputs. So I can change from here. I can see, for example, for milk, this is for milk. So as you see here, milk is increasing as you increase your daily usage of a requirement for vitamin D. For tuna and bread, they are 0. As you see here, it doesn't change. And for spinach is decreasing, as you see here. And for total cost is increasing. Very handy, very powerful, and also very easy to develop. Hope that you have also been following me and have been able to install the add installer table and have been able to run this with me. So if you wanted to do all this analysis that it did it like in a couple of seconds, it was less than 2 seconds, I think, for me. If you wanted to do it by hand, you had to run like this cellular analysis here. So 5 times to come up with these values. And for each of them, you have to plot these tables. So it would be like 5 tables as well. So it would take definitely more than 2 seconds that we do. All right, any question? What else we wanted to do? So you can actually, this is a simple model. You just have 4 fruits, 4 daily vitamin requirements. You can actually change this model and extend it in a way that you want it and really use it. So you can add, of course, it's not going to be a practical or tasty meal if you're going to have only milk and spinach and bread and tuna on your table, but you can actually add like 10, 20 more foods in these. And by adding a value, you can solve it to get the dosage, the daily dosage that we require, and also minimizing the cost. All right. Any question? We have 13 minutes almost. So I'm going to stop here.